Have you ever wondered how a miniature circuit breaker works? Welcome to a journey into the intricacies of electrical protection. Today, we're unraveling the secrets of the miniature circuit breaker, or MCB for short, a humble yet crucial device that silently safeguards our homes, offices, and industries. An MCB is a silent sentinel, standing guard over our electrical circuits. It's designed to protect these circuits from the destructive effects of overloads or short circuits, stepping in to interrupt the flow of electricity when things go awry. This seemingly simple device is a marvel of engineering, embodying the principles of electromagnetism and thermal effects to maintain the safety of our electrical systems. Whether you're turning on your coffee maker in the morning or powering up your computer for a day's work, MCBs are working behind the scenes, ensuring your electrical appliances function without hitch. So, are you ready to delve deeper? Let's dive into the world of MCBs and uncover their fascinating workings. To understand how an MCB works, we need to first familiarize ourselves with its structure. The miniature circuit breaker, or MCB, is a cleverly designed device made up of three core components: the trip unit, the operating mechanism, and the arc extinguisher. Let's start with the trip unit. This is the brains of the operation. It's the part of the MCB that monitors the flow of current through the circuit. When everything is running smoothly, the trip unit remains inactive. But when it detects an overload or short circuit, it springs into action, triggering the operating mechanism. Next, we have the operating mechanism. This is the muscle behind the MCB. Its job is to act upon the signal from the trip unit. When the trip unit detects a problem, it sends a signal to the operating mechanism, which then disconnects the circuit. This mechanism is a bit like the body's reflex action. When your hand touches something hot, your brain doesn't need to process the information before your hand pulls away. The operating mechanism works in a similar way, responding to the trip unit's signal almost instantaneously. Finally, we come to the arc extinguisher. This is the firefighter of the MCB. When the operating mechanism disconnects the circuit, it can create a potentially dangerous electrical arc. This is where the arc extinguisher comes in. Its job is to quickly extinguish this arc, preventing any further damage. These three components work together in perfect harmony, each playing a vital role in the MCB's mission to protect electrical circuits from damage. The trip unit is constantly monitoring the current, ready to alert the operating mechanism at the first sign of trouble. The operating mechanism is always ready to spring into action, disconnecting the circuit in response to the trip unit's signal. And the arc extinguisher is always ready to put out any electrical arcs that may occur when the circuit is disconnected. With the structure clear, we can now proceed to understand the operation of an MCB. The operation of an MCB revolves around two fundamental principles of electricity. Firstly, we have the thermal effect of electric current. It's a simple yet crucial concept. As electrical current passes through the MCB, it generates heat due to the resistance in the path. Now, in normal conditions, this heat is harmless. But when the current exceeds the safety limit, the heat generated also spikes. This excessive heat is used to trigger a mechanism in the MCB that disconnects the circuit, thereby protecting your appliances from damage. It's like a guardian, constantly watching over the electric current's thermal effect. The second principle is the electromagnetic effect of electric current. This comes into play during short circuits, where the current surges abruptly. The MCB contains a coil, which, when subjected to this surge, becomes a strong electromagnet. This electromagnet then pulls a lever, causing it to trip and disconnect the circuit. So, in the blink of an eye, the MCB reacts to the sudden danger and keeps your electrical system safe. Both these principles work hand in hand within an MCB. The thermal effect handles overloads, slow and steady, providing a continuous watch. The electromagnetic effect, on the other hand, is like a quick response team, ready to spring into action when a short circuit occurs. So, it's these two principles that govern the operation of an MCB. They're the fundamental laws at play, dictating when the MCB should interrupt the flow of current. And it's a beautiful thing, really. This humble device, silently keeping a vigilant eye on the electrical currents in your home, office, or wherever it may be installed. ready to act at a moment's notice to protect the entire system from any potential harm. Now that we know the principles, let's see them in action in an MCB. An MCB works in a series of steps, each crucial in protecting the circuit. Let's break down the process. The first step is detection. An MCB is essentially a guard, constantly monitoring the electrical current flowing through a circuit. It's equipped with a bimetallic strip and an electromagnetic coil. The bimetallic strip is sensitive to heat, which is generated by current. Meanwhile, the electromagnetic coil reacts to sudden surges in current. When everything is running smoothly, the current is within the safe limit. The heat generated is minimal and doesn't cause any significant change in the bimetallic strip. The electromagnetic coil also remains inactive, as the current level doesn't trigger it. However, when there's a fault, be it an overload or a short circuit, things change. An overload is when the current exceeds the safe limit for a relatively long period. This causes the bimetallic strip to heat up and bend. In case of a short circuit, the current shoots up abruptly and triggers the electromagnetic coil. The second step is tripping. This is where the MCB takes action. When the bimetallic strip bends due to heat, or the electromagnetic coil is activated by a current surge, it triggers the tripping mechanism. This mechanism is connected to a switch, which is in the on position when the circuit is functioning normally. But when the tripping mechanism is activated, it pushes the switch to the off position. This is a manual switch, which means once it's tripped, it won't go back to the on position on its own. It requires a manual reset. The final step is breaking the circuit. When the switch is pushed to the off position, it breaks the circuit. In other words, it stops the flow of electrical current. This is crucial, as it prevents any further flow of the excessive current that caused the fault. By breaking the circuit, the MCB effectively prevents overheating and potential fire hazards. It also protects the electrical devices connected to the circuit from damage due to overloading or short-circuiting. In summary, an MCB detects a fault, trips the switch, and breaks the circuit. It's a simple yet ingenious system that works around the clock to keep our electrical circuits safe. Remember, if an MCB trips, it's not a nuisance but a sign that it's doing its job. It's crucial to identify and rectify the fault before resetting the MCB. Resetting without addressing the issue could lead to serious consequences, as the fault is likely to recur, triggering the MCB to trip again. And that's how an MCB works to protect our circuits from damage. Let's summarize the working of an MCB in simple terms. A miniature circuit breaker, or MCB, is a key player in the world of electrical engineering, ensuring the safety and functionality of our electrical circuits. Its main job is to monitor and control the amount of electrical current flowing through a circuit, and it does this with an almost uncanny precision. At the heart of an MCB is a bimetallic strip, which is essentially a heat-sensitive switch. When the current flowing through the circuit exceeds the safe limit, this strip heats up and bends, triggering a mechanism that flips the switch and breaks the circuit. This instantly stops the flow of current, protecting the circuit and any devices connected to it from the damaging effects of an overload or short circuit. Similarly, in the event of a short circuit where the current suddenly skyrockets, the magnetic field generated in the MCB reacts almost instantaneously, activating the tripping mechanism and shutting down the circuit before any damage can occur. But the beauty of an MCB doesn't stop there. Once the fault has been rectified, the MCB can be easily reset, restoring the circuit to its normal operation. This makes it a reusable, reliable, and cost-effective solution for circuit protection. The role of an MCB in our daily lives cannot be overstated. It's the silent guardian, standing watch over our electrical systems, ready to step in at a moment's notice to keep our devices safe and our homes secure. It's a small device, no doubt, but its responsibility is monumental. From keeping our appliances running smoothly to preventing potential electrical fires, the importance of an MCB in maintaining the safety and efficiency of our electrical systems is truly remarkable. In the grand scheme of things, understanding how an MCB works brings us one step closer to appreciating the complex world of electrical engineering. It's a testament to human ingenuity, a perfect blend of physics, engineering, and design working together to keep our world powered up and safe. We hope you now have a clearer understanding of how a miniature circuit breaker works, a small device with a big responsibility.